So now if I collect these things into T, I get C1 plus C2 plus or minus 3 times C2. Okay, so this gives us what? This gives us, so C2 must be 1 over 3. So this is a polynomial relation. So T minus 1 equals this guy, means the constant terms gives us this relation. And once we find C2, we can find C1 because C1 plus C2 must be what? 1, right? So C1 must be 2/3. Okay, so we obtain W1 in S spaces as the coordinates of this guy is 2/3 and 1/3. And once again, what does this mean? Let me show you once again. So what this means is W1 vector, which is T minus 1 polynomial, is 2/3, no, yeah, 2/3 times T plus 1/3 times T minus 3. So this means that thing. Okay, similarly, we find W2. Let me see. Let's try to find it. So we will repeat this for W2, right? W2S. So what is W2S? This time W2 is T plus 1. And this is C1 times V1 plus C2 times T minus 3. Okay, so this time we get in T parentheses C1 plus, so same thing, right? Doesn't change, minus 3 times C2. Okay, so what does this give? This gives now C2 must be minus 1/3 and C1 must be 4/3. That gives us W2S, which is 4/3 and minus 1/3. Okay, that gives us the transition matrix. Transition matrix is now P ST equals, first I write this W1 as a column, and then I write W2S as a column, which equals 2/3 and 1/3, and here 4/3 and minus 1/3. Okay, so this is PTS. Okay, now in this part, let's take a polynomial which is 5t plus 1. Now, first, let's find T and Vs. Let's find these things. So how do we do it? So let's write 5t plus 1. Now I want to compute it. I want to compute Vt. What does this mean, Vt? So T is the W basis, right? So it will be C1 times W1 plus C2 times W2, which is C1 times W1 is what? W1 is T minus 1. What is W2? W2 is T plus 1. Okay, so this gives us C1 plus C2 is must be 5, and C2 minus C1 is 1. Okay, so what do we get? So 2C2 is 6, so C2 is 6, no 3, and C1 is 2. That means 5t plus 1 in t basis is 2 and 3. Okay. Now we can compute 5t plus 1 in S basis in two different ways. One directly and second one using the transition matrix. So let's do both ways. Okay. So let's find 5t plus 1 in S basis using the direct way. So if we compute it directly, what do we get? So this becomes C1. So what is the first vector in S basis is t and t minus 3. So C1 t plus C1 t minus 3. Okay, so from here, what we get is C1 plus C2 is 5 and minus 3C2 is 1, which gives us C2 is minus 1 over 3 and C1 is, what is C1 now? What is C1? 5 minus minus 1/3, which is 16 over 3. Okay. What does this give us? Okay, so now we have 5t plus 1 in S basis as 16 over 3, and what is this one? This is minus 1/3, right? Okay, so as another question, verify that V in S basis is equal to P S T times V in T basis. Let's verify this. Okay. How do we do it? So let's compute VS. What is PSD? We found PSD, which is 2/3, 1/3, and 4/3, and minus 1/3. Right? Let me check if I did this correctly. This one is correct. So what is T coordinates? T coordinates is 2 and 3. We found it here. Right? 2, 3. Then let's write this. Let's compute this. 2/3 times 2 is 4/3 plus 12 over 3, and this one is 2 over 3 minus 3 over 3, and this gives us 16 over 3 and minus 1 over 3. Okay, so we verified it, right? Because we found it here and we found the same thing. So it really gives us the correct solution. So this transition matrix is really used for transforming one set of coordinates in one basis to another basis. Okay. There are some few cool features of this transition matrix. One of them is so suppose okay, not suppose, but suppose that you're trying to find so you know the transition matrix from T to S, and you want to find the transition matrix from S to T. Is there an easier way of doing this, or you have to do it from scratch? There's an easier way of doing this. Not always easier, but there's another way of doing this. So the transition matrix from let's call this let's give this a name T. So name Q. The transition matrix from S to T. Okay, let's call this transition matrix from S to T, and let P be the transition matrix from let's write transition matrix from T to S. Now the relation between these two guys is really, one is the inverse of the other. Okay, this can be shown easily. So Q is, let's write this way, QTS is really the inverse of PST. Okay, and if one is the inverse of the other is also the inverse of the other one. Okay, so is this it? I think that's what I want to say about this section. I don't have any other things to say. Yeah. Do you have any questions about this section? Sorusu olan var mı arkadaşlar? Okay, so we finished this section, and also we finished this chapter. There is one more section in this chapter, and it's section 4.9. The title is Rank of a Matrix. So we don't have time to do it, I think. So if we have more weeks or more time, we can come back to this section, but I want to do some other things, okay? So we will skip this section 4.9. So if you're interested, you can read it, and to some degree, I think you can understand it. It has some important ideas, of course. So this is an important section, but anyway, we have to skip it. It's more theoretical stuff that we won't need in the future discussions, okay? But I suggest you take a look at 4.9. So let me write this. Read section 4.9, which is rank of a matrix. Okay, guys, so that's it about section chapter 4. Now what are we doing? Now we're okay, so our next topic is on chapter 6. So we're also skipping chapter 5, okay? Because some of those things in chapter 5 you will see in maybe calculus 2. Maybe you're already discussed some of the portions, some parts of it. So I find it, so this will be more useful. I think this will be more useful for us in the future. So let's go to chapter 6. Chapter 6. And here we will discuss chapter 6.1. This is about linear transformations. Okay, linear transformations. What are they? Okay, now we have two vector spaces. V and W, they are both vector spaces, okay? We have two vector spaces. So, you know, vector spaces are really sets, so we can define some functions between them. So let V be a function between these two sets, V to W. And this function will be called, a linear transformation is called a linear transformation from V to W if two conditions are satisfied. If two conditions are satisfied. The first condition is this. The first condition really says that this mapping L respects vector addition, okay? So LU plus V equals LU plus LV. This is the first condition. And the second condition says L respects scalar multiplication. So if C is a number, so let me put a vector sign here, okay? So C is a scalar here. So this is true for all. This symbol means for all numbers in R. And these are holding for every vector U and V and this vector space V. Okay, so this is also for every vector U and V. Let me put this vector symbols. Okay, so what do I want to say about this definition? Okay, let's go back. I said that V and W are vector spaces. As vector spaces, they are sets. So I can define functions between sets. So let L be a function, and we will call it a linear transformation. Let me maybe mark this, highlight this. So we will call it a linear transformation from V to W if two conditions are satisfied. The first condition is if you add two vectors and apply this transformation, it's the same as applying first the transformation to these individual vectors and then adding them. And same thing for scalar product. If you first take the scalar product and then apply the transformation, it is the same thing as first applying the transformation and then taking the scalar product. That's the definition. Now, there are some things that I also want to say. Okay, so this sum is so when we define vector spaces, we said vector addition. We talked about different vector additions, right? So we can define some exotic vector additions. This vector addition is the vectors addition of vectors in the V space, and this addition is the vector addition in the W space, because these are elements of W, okay? Because L takes from V to W. So these two additions can be different additions, okay? For example, here V is, I don't know, vectors in R2, and W are maybe polynomials. So this addition is polynomial addition, and this addition is addition of vectors in the usual space. It can be that. So we have to be careful about these addition signs. And same thing is true for scalar products. So this scalar product is the scalar product in the V space, and this scalar product is in the scalar product in the W space. They can be different things. Okay. Okay, so Now we just gave the definition, and we will see some examples of it, and then we will see why do we define such things. Okay, any questions? No. Sorusu olan varsa sorsun arkadaşlar. Okay. Let's talk about some examples. Okay, my first example is this one. Let's take a matrix, an arbitrary matrix. So let's take 2 by 2 matrix, okay, doesn't matter. So let's take A to be 2 by 2 matrix and define L from 2 vectors to 2 vectors in this way. It takes a vector U and it sends it to A times U. So the question is this: is L linear? Is L a linear transformation? Let's write it like this. Is L a linear? Is L a linear transformation? I couldn't write it. A linear transformation. Well, we have to check whether it satisfies these two conditions. So is it true that if I first add the vectors and take L, is it the same as first applying L then adding them? That's the same logic of an application. What do you mean, Nesrin? I don't understand. What is an application? I don't know what an application is, like a function. It's a special function, special type of function, right? It's not just a function. We will see that some functions will not be linear transformations and some functions will be linear transformations. Okay, so the answer will be yes. So why it is yes? So let's check it. Let's first write this LU plus V. So what is LU plus V? LU plus V is A multiplied by the vector U plus V. But for matrices, I know that I can separate this into AU plus AV, right? This is always true for matrices. And this is the same thing as LU plus LV. So the first condition is always satisfied, and the second condition also is correct. LC times U is L, what is this? The matrix A times the vector CU. Now I can always take this the scalar C outside this matrix vector product. So this is same as C times LU. So the second condition is always also holds. Okay. Any questions here? So this is this example can be generalized. This example can be generalized. So if A is like a m by n matrix, then if I define a mapping LU as A times U, then this L is a mapping from it's taking vectors in Rn two vectors in Rm, and this is always a linear transformation, okay? So as a first example of linear transformations, the matrices are always linear transformations from between Rn to Rm. This is the first example, okay? And in a sense, this example covers everything that we will see. All the linear transformations will have a representation in terms of matrices, okay? So I'm not saying that every linear transformation is a matrix, but we will see that every linear transformation has a matrix representation. So they can be represented by matrices, right? Yeah, that's what I want to say. It's like saying that every country has a map representation. Every country in the world has a map representation. I'm not saying that every country is a map, but every country has a map, has a representation on a map. That's what I want to say. Yeah. Does it make sense? Yeah. Anyway. Okay, let's look at some examples, some more examples. So, for example, let P2, let L be a mapping from P2 to, I don't know, R2. So let's define it in this way. So it takes a polynomial A0 plus A1 plus A1t plus A2t squared, and it sends it to, let's say, so it will send it to a 2 vector, which is A1 and A0 plus A2. Okay, so it takes a polynomial of degree less than or equal to 2, right? And it sends it to a 2 vector like this. So I made up this function, and I want to check whether this is a linear transformation. So is this a linear transformation? Okay, is this a linear transformation? Now you see what I said at the beginning. So so when I'm adding vectors here, I'm really adding polynomials, and when I'm adding vectors here, I'm adding I'm adding vectors in the usual sense. Okay, so the sums here, the addition signs here can mean different things. That is what I wanted to say. Let's go back to the example. Let's go back to, is this a linear transformation? So how do we check whether this is a linear transformation or not? We have to check two conditions. The first condition is, let's take one vector, an arbitrary vector, and add it to, okay, another vector in P2. So what do I get? So if I do this, first let's compute inside A0 plus B0, and then A1 plus B1t, and then A2 plus B2 t squared, right? Then how does my mapping work? It works as, so it takes the second, the component, the coefficient of t in the first component. What is the coefficient of t? It's A1 plus B1. And what is the second component? Second component is coefficient of the constant term, which is A0 plus B0 now, plus the coefficient of t squared, which is A2 plus B2. Okay, so this is L of sum of two polynomials. Now let's check the other way. So what happens to this guy? Well, let's see if they are equal or not. So what is this first guy? First guy is, what is it? It is, or it is in the definition, A1, A0 plus A2. What is the second guy? Second guy is B1, B0 plus B2. Are they equal? Yes, they are equal, right? If I add these two vectors, then the sum will be this one. So the first condition is satisfied. The first condition is satisfied. So let's check the second condition. And you can see that second condition will also be satisfied. So L times, let's check this guy. So what is this? First, I write this CA0 plus CA1t plus CA2t squared. And according to the definition of this mapping, it will be CA1 plus CA0 plus CA2. Now, what is the question? Question is whether this is equal to C times L of the same polynomial. What is this? C times A1, A0 plus A2. So are they the same thing? Yes, right? Because if I multiply this vector by C, I get this result. So they satisfy this. This mapping satisfies the second condition as well. So this is also yes. So the answer to both questions are yes, which means this is really a linear transformation. So let's write yes to the final answer. The answer to this one is also yes. Any questions, guys? Any questions? Okay, let's look at some more examples. Let's take some mapping from R3 to R2. Okay, this time let's define it as L of this vector U, let's call this UVW, no, let's call this XYZ. So let's define it as X plus 1 and 2Y. Question is the same. Is L linear? Is L a linear transformation? Let's write it like this. Is L a linear transformation? Please think about it for a minute, okay? Any ideas? No. Yes, the answer is no. Thank you, Barış Azar. Let's see why the answer is no. Okay, so I'm checking the first condition, right? First condition says the first condition says if I first add the vectors, let's add it to ABC. So if I first add these two vectors, what will I get? So this will be x plus a, y plus b, and z plus c. And what is the final answer? So it's if I apply the transformation L, I get the first component plus 1, and the second 2 times the second component. Okay, now let's apply it separately. So let's first compute x, y, z, and then add it to L of a, b, c. So what will it give us? It will give us x plus 1 and 2y plus what is LABC? It will be a plus 1 times 2b, right? So if I add them, I get what? I get x plus a plus 1 plus 1 is 2. Okay, so you see, in general, these two things are not equal. In fact, they are never equal. They are not equal, right? Because the first component of this guy is 1 more than the first component of this guy. So they can never be equal, which means this is not a linear transformation. Okay, so you see what is destroying what is destroying being a linear transformation is this extra factor plus 1. This 2 is okay. You see the second components, there is no problem in the second component, but there's a problem because of this plus 1. We will talk about this more in other examples. So in a linear transformation, this is not allowed. Okay, adding constant terms is not allowed in linear transformations. So it destroys being a linear transformation. Let me know if you have any questions. So what did we see here? Let's write what we have seen here. Oops. So where is this? So we have seen that L u plus v here is not the same as Lu plus Lv. So this is not a linear transformation. Let's write no as answer. Var mı sorusu olan arkadaşlar? Let's look at another example. This time, let's talk about row vectors, okay? So there's not much difference between row vectors and column vectors. In row vectors, I write, what is this? I write this row vector as a subscript, okay? So let's define L in this way. It takes a row vector, let's call this x and y, and it sends it to x squared, and let's call this y. So the question is same. Is L a linear transformation? Okay, let's think about this for a minute. Okay, let's think about this. Let me know what you think. Any ideas? What do you think? No. Okay. Okay, I think it's no. Let's see why. Uh, so okay, so we're checking whether the, so we can also work with examples, right? So it doesn't matter. So let's just check L 10 plus L 20. Let's first add these two things and whether check that this is equal to L 30. If it is not equal, then the condition will not be satisfied. Okay. If it is, if this condition is satisfied, of course, we cannot say this is a linear transformation because we picked an example. But if it is not satisfied, then it shows that it is not satisfied for every vector and it is not a linear transformation. Okay, so we can only derive one conclusion from here. If it is not equal, then it's not a linear transformation. If this is equal, maybe it's just a coincidence. But we will see that it's not a coincidence. So what is L10? L10 is, let me do it like this. What is L10? L10 is 1 and 0, right? What is, let's write plus. What is L20? It is 4 and 0. So this answer is 5 and 0. But what is L30? L30 is 9 and 0. So these two things are not equal. Okay, so what does this show us? This shows us for these specific vectors, this condition is not satisfied. And if this is not satisfied for like one choice, then this is not a linear transformation. To be a linear transformation, it has to be satisfied for all choices. Okay, so this is not a linear transformation. Okay, questions? Okay, once the first condition is not satisfied, I don't need to check the second condition because this can no longer be a linear transformation. Let's look at one more example. This time, I'm considering a linear transformation between polynomial spaces P1. So P1 has polynomials degree less than or equal to 1, and P2 has polynomials less than or equal to P2. Let's define L of L of PT. What is L of PT? This is, let's define it T times PT. So the question is L a linear transformation? Okay, let me stop for a minute again and let me know what you think. What do you think the answer is? So let's try no to hit this one. This is no. Okay. Let's check the first condition. Let's take two polynomials p, and let's consider the polynomial q. And if I add them, what do I get? So the answer will be t times pt plus qt. But now I can multiply this by t, right? So this is tpt plus t times qt. And t times pt is what? T times pt is lpt. T times qt is L of qt. That's the definition. Okay, so the first condition is verified. So this is the first condition. It holds. The first condition holds. What about the second condition? L C times pt. Let's first consider this one. So by definition, this is t times cpt. And what can I do? I can take this c out, right? And I can write this as t times pt. But t times pt is really lpt. So the second condition also holds. So both conditions are holding here, which means this is a linear transformation, okay? So the answer is yes. Any questions here? No? Okay, we have a few minutes. So let me write an important property of linear transformation. So if we have a linear transformation between two vector spaces, then we have these two properties. Then the first property is, okay, so the first property is L must take the zero vector in the V space to the zero vector in the W space, okay? So they can be different vectors, of course. Zero vectors here can be different from the zero vectors in the W space. If V is the space of matrices, this is a zero matrix, and this is a, I don't know, vector space of polynomials, then this is the zero polynomial. So they can be different things. But this must hold for a linear transformation. And the second thing is also straightforward, and it says that if I consider the difference between two vectors, then the property of linear transformation extends to difference. Okay, so I can write this in this way. So both of these conditions are easy to prove. They are very easy to prove. So let's just go back. Let's just go back, for example, to this example, to this example, x squared 1. No, not this one, I'm sorry. Let's go back to this example. So if we took 0, 0, 0 here, then the result should be, the result will be 1 and 0. So it takes the 0 vector, but it sends it to a vector which is not the 0 vector. Okay, which means that this cannot be a linear transformation. Okay, so I will talk about this tomorrow, and I will write these things tomorrow again. So let's stop here, and if you have questions, you can ask now. If you don't have any questions, you can leave the meeting now. Okay. Yoklamayı buradan çekiyorum arkadaşlar. Sistemden otomatikman çekiyorum. Yani burada herkesin ne kadar katıldığı, ne olduğu falan görülüyor zaten. İyi günler arkadaşlar. Herkese görüşmek